you're welcome to ask me questions during these recitations. And now I will share my screen. So today's recitations is uh, still on the topic of graph neural networks. And during the last lectures, we have already introduced the permutation invariance and how the message passing process work. And today we're going to have a quick review of the GCN message passing process, and then we will derive the graph convolution layers forward as well as backward. Based on that, we will give GCN code examples to help you start to build up your own GN codes. And we will use the package of PyTorch geometric. Okay. So before we move on to the math parts, let's review what we have learned in the last lectures. So during the last lectures, we have learned that single GN layers is generating the node embedding based on the neighbor environments. And during the node embedding generation, we are doing the feature aggregation based on the neighbor information. And basically what's happening in the feature aggregation is given a interest node, and if we consider a single step of feature aggregations, we are aggregating the first nearest neighbors informations together and combine it, merge into a new information and assign it to the node that we are interested in. And there is so after the first iteration of feature aggregations, the target node will be aware of the information of its first nearest neighbor. Besides, we don't want to lose the information of the node B itself. So we have to add a self loops to make sure that the information of B is passed is remain during the feature aggregation process. And if we follow in the same manners, after the second step of feature aggregations, the node B will be aware of its second nearest neighbors as well as its first nearest neighbors during this message passing. And besides, we also discuss about how to combine and merge the information of the neighbors. The way is, first, we use a pooling function like sum or products or mean or max or minimum. And then we use a neural network to map or merge the pooling informations into the desired shapes of the node B's, and we assign it to the node B. So, and also for the graph convolutions, we usually use mean as the pooling functions for merging the node feature. So based on this, we know during one iteration of graph convolution, if we apply the same feature aggregation to every node within the graph, then it will become a graph neural network layers. So this is what we discussed during the last lectures. And now we will continue on and derive how the forward and backward layers of the graph convolution will be like. So Sorry, no, so first is the before we start to introduce the matrix form of the single layer of graph convolutions, let's first take a look at the uh, scalar form of the graph convolution. So here, consider we're still interested in a single node's feature aggregation within the graph, and we're interested in node B. So the things we need to do is we first aggregate all of the first nearest neighbors information as well as the information of B itself. And we use the mean to pull the information and apply neural networks. Mathematically, what's happening here is, so here the V zeros is stands for the zeros layers embeddings, which is the initial states of the node B, and it will equal to the node feature of B itself, and it will have a shape of one by f. So f here is the feature dimensions. The one here stands for a single node B, and this shape will be the node features embedding shape of the node B. So if we consider the time step t plus 1, so it will equal to the feature aggregation of the nearest neighbor and the node B itself. So we separately dealing with the neighbor nodes and the node B. So on the left-hand side, you can see here, there is a weight terms and also a sum terms. So within the sum terms, you can see this HUT here is the first nearest neighbors of node B, the node information of the first nearest neighbors. And after you sum up all of the first nearest neighbors, you need to divide it by the number of the neighbor nodes. So this is the mean pooling here. So we are doing the sum, and for each node features, we divide it by the number of neighbor nodes to do the mean poolings. And after that, we apply a weight terms. And one thing you need to pay attention is this weight terms is a learnable weight. So after that, on the right-hand side, we will only need to deal with the node B itself. So this HVT is the node feature matrix of the node B at the time step t. So pay attention. So this is the node feature embedding of the B at time step t, and this is the time step t plus 1. So they are different. And similarly, we'll also apply a learnable weight terms here, which is B. And after that, we sum up these two terms and pass it into a nonlinear activation, and it can be a ReLU or sigmoid here. So this becomes a scalar forms of graph convolution for single layers. So does anyone has any questions about this equation? Okay, since that we will move on. And now what we want to do is based on these scalar forms of forwards, which we will try to rewrite it into a matrix form. So still, we want, so still first we need to uh, let's first take a look at these H terms. So for each node within the graph, the node features matrix will have a shape of 1 by f. But remember, during the single layer of graph convolutions, we will apply the similar feature aggregation manners to all of the nodes at the same times. Consider that we are doing the feature aggregations for these graphs, and there will be 6 nodes within the graphs. So the shape of the node features will become n by f's instead of the 1 by f, because it represents all of the node features within this graph. And now the things we need to do is, how can we transform these sum terms, these normalized terms, and these learnable weight terms into a matrix form? And besides, we also have two types of node information: the neighbors and the node itself. So the way we do that is first we have the node feature matrix, and now to perform the feature aggregations, or to say aggregate some of the neighbor nodes informations to the target nodes itself. What we need to do is we multiply the adjacency matrix of these graphs on the left-hand sides of the node features matrix. And this is a very basic operations in the graph series if you want to aggregate the neighbor informations to a target nodes, and you want to conduct it into with respect to the whole graph. And so these two terms make sure that you do these sum operations. And to do the normalization terms here, which is divided by the number of the neighbor nodes. One thing you can do here is, so of course you can use the scalar form to directly divide this product matrix with the number of neighbor nodes. Another way is you can create a diagonal matrix with all of the elements as the diagonal lines equal to number of nodes one divided by, yeah, sure.
Yeah, it seems like your slide is not changing.
Sorry. So which page can you see for now? So
your slide is just stay on the first page.
Okay. Sure, let me can you see the slides?
Yeah, I can see it now.
Sure. Okay, so so here is the graph. Okay, so now we have discussed that to do this sum operations, we multiply the adjacency matrix on the left-hand side, and to do the normalizations, we create a diagonal matrix with elements equal to 1 divided by number of neighbor nodes in the diagonal lines, and the product matrix of these three terms will be the terms within this red lines, red square. And after that, we still need to uh, uh, deal with this learnable weight terms. So the way you do with this learnable weight terms is you multiply the learnable weight on the right-hand side of the node feature matrix. And here, we need to pay attention to the shape of each matrix. So because our feature matrix have a shape of n by f, so n here stands for number of the node, and f here stands for the node features dimensions. So for the H matrix at every time steps or every layers of the graph convolutions, it will have a shape of n by f. So we need to make sure after the all of the operations, the product matrix will still have the shape of n by f. And we can check that like the adjacency matrix have a shape of n by n, and the normalizing matrix also have shape of n by n. So on the left-hand side, the shape will remain n, and on the right-hand side, because the weight matrix has the shape of f by f, so the final products matrix will have the same shape with this node features matrix, and this makes sure that the node feature matrix doesn't change its shapes during the feature aggregation process. And there's one thing we need to pay attention is, so now what we deal with these learnable weight terms is we multiply the weight terms on the right-hand side, but and we assign the weight terms with a shape of f by f. But if we multiply the weight terms on the left-hand side, and assume that we assign the shape of the weight matrix to n by n, it can still produce the node feature matrix with the right shape. But this is a wrong version of operation to write the graph convolution layers. So the reason is, if we multiply the matrix on the left-hand side, so this matrix is kind of similar with the adjacency matrix. If we look into the details of the matrix multiplication, we can see that during the matrix multiplication, you multiply each row of this matrix with the columns of the node feature matrix. And this way of operation is mixing the information among the different nodes. And it is very similar to the way that the adjacency matrix do. So this will make the process become, this will make the weight matrix become a little bit redundant. Because ideally, we want to use the adjacency matrix to mix the informations among the different nodes. And we want to use the weight matrix to mix the information within the single nodes. And what does it mean by within the single nodes? Let's see the next slide. So still, if we look into the details about the matrix multiplications, so when I put this weight matrix on the right-hand side, we are multiplying the row in the node feature matrix with the columns in the width matrix. And this makes sure, and also after this multiplications, we are using a so this is a learnable weight. So this operation is exactly the same as a single layer of MLP. So this MLP is mixing the features. So what the features is it mixing? It's mixing the feature within the same nodes. So in this way, uh, uh, with the adjacency matrix on the left-hand side and the node feature matrix on the right-hand side, we can reach the effects of mixing the features among the different nodes and within the single nodes. So that's why we put the adjacency matrix and the weight matrix separately into right and the left part of the node feature matrix. So by now, does anyone has questions about the things I discussed before? Okay, then we will move on. And finally, for the terms wrote in within these red lines, the matrix multiplication will be written down as this form. So here's we have a normalizing matrix, a adjacency matrix, and the node feature matrix, and finally a learnable weight matrix. And it will merge, it will produce a new node feature matrix with the same shape of HT. And another thing is we need to deal with this self-loop terms. So the self-loop terms, one of the easiest way to deal with it is, so now first we have this, we still have this node feature matrix. And since the self loops is passing, is only passing the node features to itself, we can still represent it in a adjacency matrix. So in adjacency matrix, this kind of connectivities and message passings can be represented as a identity matrix. So if you multiply this identity matrix with the node feature matrix, you are doing the self loops message passings over the graphs, over these graphs that we are interested in. So specifically, if you look into it, so the identity matrix only have the elements in the diagonal lines equal to ones. So the elements in the diagonal lines are stands for the connectivity between all of the nodes and itself. For example, the B is connected to the B. So after you multiply this matrix with the node feature matrix, it will finish the self-loop message passings. And similarly, we will apply a learnable weight terms with the shape of f by f here. So because here these terms we do not need to normalize it, so we don't have a normalizing terms here. We only need the product of these three matrices and produce a new feature matrix. So this is how we deal with this self-loop terms. Okay, so after we discuss the things above, we can rewrite the equation above here, which is the feature aggregation of a single node, into the matrix forms below. So this matrix form is how the graph convolutions doing the feature aggregations for every node within the same graph at a single graph convolution layers. So within the parentheses, there's two terms. The left terms is aggregating the neighbor node features and doing the normalization and apply a learnable weights. And the right terms is doing the self loop message passing to pass the node features to itself and also apply a learnable weight terms. So after we sum up the two information, we apply a nonlinear activation sigmoid here, or other nonlinear activation. It doesn't matter too much, and it will produce the node feature embeddings of the next of the layer at time step t+1. So this besides this so now we have already read down in these terms. We can apply a single trip and take one step on to combine these two terms. So recall that for the no matter for the node feature aggregation or the self loops, we all multiply the node feature matrix with adjacency matrix. So because the adjacency matrix are different due to the operation we are interested in, for the neighbor feature aggregations, the adjacency matrix show the connectivities of one node with all of its neighbors. And for the self loops, the adjacency matrix only contain the connectivities of every node with itself. So if we sum up these two adjacency matrix, it will become a new adjacency matrix which represent every edges of this graph, as well as the self loops of each nodes. So we can apply these tricks and merge the adjacency matrix together here, which is the A hat. So A hat is the sum of A and A prime. And now we rewrite a new learnable weight term, which is W prime transpose. And finally, these two terms will be rewritten as one terms here. So the only difference is this adjacency matrix term and the weight terms. So the node feature terms are the same, and so did the normalizing matrix. And this is the forward equation of a graph convolutions. And if we check the shape of the equations, the normalizing matrix is n by n, adjacency matrix will be n by n, and the node feature is n by f. The weight matrix is f by f. The products of this matrix will still be n by f, and it's the same with the h t prime. Is there any questions? Because we need to understand how we get these equations, and then we need to move forward to the backward parts. Okay, so now I will switch my screen to my iPad and derive the backward of the GCN layer. Uh, can can everyone see my screen?
Yes.
Yep.
Okay. Okay, sure. So you can see this GCN backwards parts, right? Okay,
Yep.
now let's derive the GCN backwards. You're welcome to ask me any question within this process, okay? So before we start to so during the GCN backwards class, so we will derive the backwards for these equations. So before we start to derive doing the derivative for these equations, let's recall some basic matrix derivatives rules during the MLP and linear layers. So consider that so we have a matrix form equation here like this, and let's assign a shape to each of the matrix. Let's say this is 4 by 2, 4 by 3, 3 by 2, and say that I know the d loss over dy. So this term is known. And we want to solve the d loss dx and d loss d omega. So with the chain rules, the way we solve the d loss dx is equal to first d loss dy and multiply the dy dx. So here is the matrix multiplications, and there's another operators we use is the element-wise products, and we need to tell the difference between them. So these terms, because these terms, so if we write the matrix form in this form, and these terms will equal to exactly omega transpose. So let's check about this. So d loss dy will have a shape same with y, which is 4 by 2. And this terms, so the weight transpose will be 2 by 3. And the result matrix will have the shape 4 by 3. So this will be the same with the shape of the X matrix. So we are doing it right, and it will be okay. And the other terms here, d loss or d omega, will be so. Because in this kind of orders, it's hard to directly get these terms. So the way we solve these terms is we take the transpose of the original equations like this, and it will becomes y transpose so the transpose can help us sweep the orders of x and omega. Sorry, the w terms, not omega. And with these equations, we can first write the d loss over d omega dw transpose equal to, so based on these equations, it will equal to d loss or the y transpose and multiply the dy transpose dw transpose, and these terms will be equal to x transpose transpose. So the result will be d loss dy transpose multiply x. And so this is, so this terms is d loss dw transpose, because d loss dw equal to d loss dw transpose transpose, and we can transform this inner terms into, so it's equal to d loss dw transpose. And finally, we can write the terms we are interested in as d loss d x transpose multiply x. Right. So these equations and these equations are the equations that we are going to use in the GCN backwards. So first, before we move on, let's check the shapes to make sure that we're not making any errors. So here, we have already checked shape for this, and for this, d loss over dx transpose have the shape of 3/4, and so the x has the shape of 4 by oh, sorry, I wrote one terms wrong. So this is y transpose, and this is the y transpose. Okay, so this will have a this term x. X is 4/3, and d loss dy transpose will be 2/4, and the result shapes will be 2/3, which is exactly, and after transpose, it will become 3/2, which is exactly the same shape with weight terms. So now we have already finished these parts, and let's start to derive the backward for GCN. So I think the GCN is not that difficult as the CN backwards. So the only thing we need to do is draw a computational graph and derive it based on computational graph. So let's rewrote our equations here. And the shape of each terms is so now here the n denotes the number of nodes, and f denotes the number of node features. Okay. So first to make this equation more easier, I will define two terms. So the first terms is I want to wrap up the things within the parentheses. So let h delta equal to d a h t primes with transpose. Okay, so this create one node in the computational graphs, and the other things is I want to define a terms that represents the product of these two matrices. Let's say h delta 0 equal to the products of ht primes and the w prime transpose. So the reason I define it this way is because the normalizing matrix and the adjacency matrix, they are the constants matrix in the GCN forwards. And we only need to take the derivations for the node features terms and the weight matrix terms during the back propagation. So the target terms we need to solve is d loss over dht primes and d loss over the w prime transpose. Okay, and now let's draw the computational graph. So the ht primes ht primes will be decided by the h delta, which is the terms within the brackets, and h delta will be defined by the constant matrix terms as well as the h0 delta here. h0 delta is defined by the ht primes and w primes transpose. And let's mark the shape of each matrix. H delta is okay. And now we already know the d loss over dht plus 1. The things the terms we want to solve is d loss over these two terms. So first, this process is only an activation. So during the back propagations, this first propagations, okay, the d loss over dh delta is equal to d loss over dht plus 1. Element-wise products, the dh t plus 1 over d
H tilde. Okay. And this is the back propagation through these activations. And after that, we do not interested in these terms, the derivative of this term. So we directly back prop through this road. And so the next step is d loss over dh0 tilde. So the d loss over dh0 tilde is so let's see. We need to refer first. Let's write down the equations here. So the h tilde is the constant matrix multiply the h0 tilde. And this is so this is very similar to what we recall just now, the y equal to x w. So in this case, the h tilde is in the same position with the w. So we can write down the derivative of the d loss dh0 will be equal to d loss over dh tilde plus the constant terms and then transpose. Okay, so now we have already got the derivatives for the dh tilde here, h0 tilde, sorry. And then the questions reduce to a single affine equations like this. So first, let's write down h0 tilde equal to ht prime and w prime transpose. And we have already computed the d loss over dh h0 tildes. So the rest things we need to do is take the derivative of these two terms. And still, using the result we have already derived from these equations, we can write down two terms as d loss over. So because this part is all the same with the previous pages, so I will just directly write down the results. And d loss over dh tilde t plus the matrix ht prime. Okay. So basically, the GCM backwards is just first construct the computational graph and then using the basic matrix derivatives to do the backward propagations. And the most important things is we're only interested in the derivative of these two terms. And this matrix will be treated as a constant. And this is the GCN backwards. So does anyone has questions about this part? Okay, since that, I will move on to the last part of today's recitations.
So the next part will be the an example code for the graph evolution. Let me open my Jupyter notebook. Can everyone see the Jupyter notebook? Can you hear me, guys? Okay, sure.
Yeah.
Okay, sure. Yeah. So this is an example notebooks for example notebooks for using the PyTorch geometric to build up the pipeline for GNNs. So since we don't have a lot much times left, I will quickly go through it, and then it will be upload to the course website, and you can use it, explore yourself. So here is the official website of the PyTorch Geometrics, and so PyTorch Geometric is a package that built on PyTorch and have some built-in functions for GNN and for different types of GNN layers, and as well as the dataset data loaders. So usually it's very popular in GN trainings and some GN related things. And so as you can see here, if we want to train GN first, it's about the data loading parts. So as we can see in the as we can see in the GSyn forwards, usually to represent a graph, we need an adjacency matrix and a node feature matrix. But practically, so for the node feature matrix, if you want to use this to store graph information, there's no problems. But usually, the graph that we are dealing with is sparse graph. So sparse graphs means most of the elements in the in the adjacency matrix are equal to zeros. So this will raise a problems about the waste of the storage if we use the adjacency matrix to store the connectivity of the graph. So usually in, in PyTorch matrix, the way it stores the graph is it only uses the connectivity between the different nodes. So so for examples, here is a graph and it has 4 nodes, 0, 1, and 2, 3. Instead of using a adjacency matrix, it represents connectivity with a 2 by number of edges tensors. So here you can see 0 is connected to 1, 0 is connected to 2, 0 is connected to 3. And this is exactly the same within the graph. So this way, so if you store the graph in this way, it will save more of your space in your computers. And this is how the PyTorch metric store a single graph. And of course, this X is the node feature matrix. So here you can see there's a 4 nodes, and each node has 2 dimension of node features. And also another issue is how to store a batch of data, a batch of graph data. So the way PyTorch metric do it is for a batch of graphs, because it has a adjacency matrix and the node feature matrix. For node feature matrix, we can just directly concatenate them along the certain dimensions. And for the adjacency matrix, it just diagonally concatenated each adjacency matrix, which means a batch of graphs will be treated as a single unconnected graphs. So each subgraph stands for a single graphs of the original data. And PyTorch metric has an abstract class called message passing. So this message passing is kind of similar with the N modules in PyTorch. So you can use the message passing class to define your own message passing equations. So like you can see here, it will include a message, an aggregation method, and updates. So if you change the way of update, aggregation, and the message, you can code it your own graph neural network layers yourself. And GCA is only one of the subcase of this general framework of feature aggregation. So now today's I prepared one of the examples mentioned in the last class. So is the molecule property predictions. It's also known as a graph level classification or regression problems. So if you still remembers, last time during the lectures, here's a one problem as an introduction that we want to predict the carbon dioxide solubility of the ionic liquids. So usually one ionic molecules compose two, one ionic liquid compose 2 ionic molecules of different charge, which is cations and anions. And we can abstract it to a graph. And this graph will represent a single data points. And the data set we're using contains 10,000 of data points. So each data points contains the structure of the cations anion, which is the graph here. And also it contains the temperature and the pressures. So the following codes is doing the property prediction the training and also the property predictions for the ionic liquids. So as you can see here, you need to make sure that you install all of the packages listed in the cells. And here is some arguments. You don't if you don't need to change the arguments here, the data path arguments here, as long as you download the whole handouts. And there is some already written functions for data processing. And here, this N module class is where you define your models. And as you can see here, I only include one single GCN layers here. And you can expand it as your, depending on your needs. And after that, here is some training utility functions. So if you, and also there's a plot functions. And if you train the models, and then you can test the performances of the models. So here in this demo, I only train for one epoch, and the model is very simple. So obviously it does not have a very good results. But you can make the model larger and then train more epochs and to test if there will and test about the difference. And there's a final cell to help you plot the results. And that's all for this Jupyter Notebook demo for the graph convolution for the graph neural networks. And that's all for today's recitation. So does anyone has a question about the things I mentioned before? Okay, great. So thanks everybody for attending today's recitations, and I'll stay here a little bit and for the questions.